Now we will try to understand theoretical basis for dispersion. We will do this in the framework of elementary theory of dispersion. Elementary means that we will apply some simple approach and this approach will be based on a model. This model will be as follows. We will assume that electrons in atom are bounded in atom by elastic links, and these elastic links allow electrons to oscillate. When this electron is influenced by incoming electromagnetic wave, this force from electromagnetic waves, here we have, for example, in this direction we have electromagnetic wave which has E vector oscillating and H vector oscillating, and when they arrive to atom, a force is exerted from the side of electromagnetic field, and this force makes electrons to oscillate. Look, these links are quasi-elastic, and in this case we can compare what is happening when we have a classical oscillator, and if we have classical oscillator and this is x axis, and we have some body of mass m and the spring with some coefficient kappa, then if we shift this body, so we have some force which is minus kappa x. And if we apply some external force to this system will oscillate with a frequency of the external force. It is common for all forced oscillations. What is, in our case, what is our external force? External force appears from electromagnetic field, and this force is Lorentz force, and Lorentz force, we know it from electricity, and it is minus EE and minus EVB. It can be shown that V will be small enough in this case, and as far as V is small, we can disregard this term and consider only this part of the force, and say that this force which is exerted on electrons from the side of electromagnetic wave is approximately minus EE. Then if electron is shifted from its equilibrium position, total force will be this one plus quasi-elastic force, and then we can say that we can write down an equation which is known equation, Newton equation from mechanics, and it will be m r2 squares, 2 points, the second derivative from r is displacement of electron from its equilibrium position is equal to minus this force E and minus kappa R. Now we can rewrite this equation. We can rewrite this equation. We can first of all, we can suppose that the displacement is in the same direction as E, this displacement. So we can have a projection on this direction and write down this equation already without vectors. And in this case, if we divide by m and transfer this term left part, we can rewrite this equation as r, the second derivative on time, plus omega 0 squared r is equal to E divided by m, here is minus, and E of time. This E, this is field which is produced by electromagnetic wave. Well, what is omega squared here? Omega 0 squared is omega 0 squared is kappa divided by m. Here, if we divide by m. What is E on T? E on T is electromagnetic oscillations which are cosine omega t plus alpha. Look, here we wrote oscillation, not wave, because this is what is happening with electron. Electron is located somewhere at some distance from a nucleus, and in this point the field which from this propagated wave, it reaches this point and produce in this point these oscillations of E. This alpha stands for initial phase, and initial phase in these oscillations is different for different electrons, just because electrons are located at different coordinates. So wave reach these points at different time. So the oscillations, vibration of electron here and here will be shifted by some phase alpha. We can assume that these oscillations of electrons are which are produced by initial force result in emission of secondary wavelets by electrons which are oscillating, because any charge particle which moves with acceleration emits electromagnetic wave. So in this case, secondary electromagnetic waves. It is evident that some energy is spent in order to emit this wave, and so actually all this vibration should attenuate with time, and this damping we can neglect, at least in this simple approach. In principle, we need to add to this equation some additional force which is proportional to velocity of electrons, and it is equivalent of friction in mechanics. But again, we will, at the moment, we will disregard this additional term in the equation. Now, if we substitute this Okay, here I omitted some amplitude. Amplitude should be E0. So if we substitute this force here, we will have the equation, which is r, the second derivative on time, plus omega 0 squared r is equal to minus E over m, E0 cosine omega t plus alpha. We need to resolve this equation. From a mathematical point of view, it is easier to resolve it in a complex plane. In order to make it complex, we can add to the right side of this equation some imaginary part imaginary part of the form minus I E over m E0 sine omega t plus alpha. When we did it, we immediately make left part already complex. So I will not add it immediately, but I say if we add this part, if we add this, then we will have next equation, which will be r, this will be complex, and second derivative, plus omega 2 squared, and r is again complex. I will denote it with this, and it is equal to minus E over m, E0 complex, and E I omega t. What is this complex amplitude? This complex amplitude E0 is equal to E0 and E minus I alpha. Now we have this equation, and we will seek the solution of this equation in a form of r is r0 complex E I omega t. Here R0 is a complex amplitude of oscillation of electron. We need to substitute here the second derivative, and the second derivative, if we take it from here, we see that R second derivative, R complex second derivative is minus omega squared, R0 derivative, so complex, and E I omega t. Now we substitute this and that in the equation, and we obtain the following equation: minus omega squared R0 E I omega t plus omega 0 squared R0 E I omega t is equal to minus E over m E0 E I omega t. We substitute these terms in this equation. Now we can rewrite it in the following form: E I omega t R0 is equal to minus E over m E0, and and here omega 0 squared minus omega squared and e I omega t. So we see that E0 complex amplitude multiplied by this E omega t is actually complex initial electromagnetic wave. Then this E I omega t R0 is R, here is R0. So we can R complex. So we can arrive at the equation that R complex of T is minus E on M, E complex on T of T, and omega 0 squared minus omega squared. Now if we go back to real numbers and we'll take only a real part of this, we will have, from this we will have that real R of t is minus E on M, E of t, and omega 0 squared minus omega squared. Now if we look what is happening, this is R of t. What is the physical sense of this value? This is displacement of electrons under the external force E of t. E multiplied by E of t gives us electric force, and this is displacement depending on time. What will happen when electrons will be moved along this direction, and electrons are minus E and here is plus. So it is evident that in this the result of this will be polarization when we have some shift of electrons against minus charges against plus charges. If we have a molecule which contains many atoms and consequently many electrons, for molecule we will have a dipole moment of molecule with after this polarization will be equal to this is summation over all the atoms in molecule, and in molecule we have atoms which consist of nuclei and electrons. We will denote L will be index for nuclei, and nuclei have charge Q, L, and center of this nuclei are R0 when no external force is exerted on molecule. This is for nuclei, and in addition to this we have a lot of electrons which surround this nuclei, and here we will have summation over all electrons. Each electron has charge Ek, but this Ek is of course minus, and the displacement is against initial position. Initial position is R0k, and the actual coordinate will be this initial position plus, for this specific electron, plus Rk on T. where R of t is here. Now we can rewrite this. Just we will group these terms which belongs to equilibrium, location in equilibrium of atoms and electrons and nuclei, and this shift against the points of equilibrium. Then we will have sum of L, QL, R0L plus sum on K, EK minus R0K. This will be one term, and another will be this shift against equilibrium for electrons. Now look, what is here? We remember that molecules in substance can be of two kinds, polar and non-polar. We will assume that we deal with non-polar molecules, and in this case this is dipole moment of non-polar molecule, because this is QLRL, this is positive charge and this is negative charge, and in polar molecule for zero this means stable position in equilibrium, and this gives us zero because non-polar molecules have without external field have no dipole moment. So this dipole moment, this is pi p 0, and it is 0. And this is the only term which produces this external, this additional dipole moment, and it is equal to sum on K, EK minus EK, RK of T. Now, it is a safe assumption that RK at any moment is parallel to EK, E external. Indeed, we can assume that all electrons are shifted by the field in the direction of the field. Then projection of a dipole moment on the direction of E is P on T is sum on K minus EK RK of T. And in this case we have now additional point which we have to take into account, that now we put here symbol K and here as well. So what is this symbol K? What is different on, for all electrons? It is again our assumption, and it is correct assumption, that each of electrons will be will have its own frequency. This term omega 0 will be for each of electrons can be different, m is of course for each of electrons the same, but this coefficient may be different depending on the distance between electron and nucleus in atom, because the greater is this distance, the lower is this force, smaller is this force. So it means that this kappa is different for different electrons. So each of electrons will have its own displacement Rk. Then what we had here, this means that all this omega 0 squared has to be added symbol k in our equation. I'm not sure that you saw what I mean, that electrons are at different distances, and so kappa is different because this force is different. Well, so we put here k, and when we sum all the terms, we will have that P on T is equal to sum on k minus E. Okay. All electrons, of course, have the same charge, so this k we can omit, because all electrons, everywhere this is a charge of electron, not something else. So that is just minus E, and as R we have this minus E on M, E of T, and here is omega 0 k squared minus omega squared. So this is equal to sum on k E squared over M E on T omega 0 squared, and here is index k minus omega squared. Now let n is number of molecules in the unit volume, then n p on T of T is P on T. Here is polarization of material, of substance. On the other hand, we know that this polarization is epsilon 0 kappa E. This we know from electricity. And P is in nonpolar molecule is in the same direction as E, so projection on this direction is also can be written in this way. From here we can substitute E here by E is P divided by epsilon 0 kappa. Or on the other hand, we can substitute kappa, and kappa is P divided by epsilon 0 E. This is what we need. Why we need it? Just because if we again recollect what we know from electricity, and we know that epsilon is 1 plus kappa. Now we can substitute kappa from here. In order to obtain kappa from here, we can say that this is 1 plus then P on T divided by epsilon 0 E. But polarization, this is 1 plus, but polarization is this value, P on T, multiplied by N. So we can say that this is N divided by epsilon 0, and here P on T is this term here. So it is P on T sum E squared on M, and E, here is E, here is E. They cancelled, and in denominator what remained is omega 0 K squared minus omega squared. And this summation is made on K index. Okay, but we know that epsilon is n squared, where n squared is a refraction index. Then we see that as far as omega is far from omega 0K, this denominator is large and this term is small. In principle, if this difference is very large, this is 0, and epsilon is 1, and epsilon is 1, and epsilon is n squared. In the case omega tends to omega 0K from left, then it is less than this number, and we see that in this case epsilon tends to infinity, in infinity plus infinity. When this omega tends to omega 0 from right side, it goes to minus infinity. So if we plot a graph, then we will have something like that. This is n squared, this is omega, this is some value omega 0, 1, somewhere here is omega 0, 2, and so on. And this level is 1. Then, as I already said, here we will see something like this curve. It goes in infinity, and from this side it comes from infinity and goes this way to 1. And again here we will see the same, it will go to infinity, and here this is what is predicted by our elementary theory. But the question arises how it is possible that n is going to infinity or minus infinity. The answer is that it is not possible. And why we obtain this result? We obtain this result just because we neglected this dumping of oscillation due to emission of electromagnetic waves by accelerator electrons. If we take into account this so-called friction of electrons or loss of energy by electrons during oscillations, this curve will have the shape like this. And this is what in reality is observed. And if we are far from this resonance frequencies, we see that in this case n squared is close to 1. And in the vicinity of these resonance frequencies, we have different situation. Situation is this dramatic change of the uniform change of n squared. It is possible, of course, as far as omega and lambda are reciprocal. So in this case, we can transform our graph to the case of lambdas. And if here it was for frequencies, it was this way, then for lambdas, what I mean that they are reciprocal, I mean that lambda is 2 pi c over omega. So if that graph was omega n squared, so if we put here lambda 0, this is lambda 0 of course, if we put here lambda 0 and here we'll put n after taking square root from that, the curve will be again similar to previous one. This will be 1, but the shape will be not this one, but mirror. So if we have here we have lambda 0, then the curve will be like this. If we look at this curve, we see 3 different regions. One region is here, and in this region we see that the dependence of n on lambda is corresponding to normal dispersion, because for normal dispersion we have this dependence n on lambda 0. So here we have in this region and in that region we have the behavior of n, which corresponds to what we called normal dispersion, and in this region it is anomalous, and this region corresponds to resonance in oscillations of electrons. And in the case of resonance, the absorption is very, very significant, and in this case this anomalous dispersion corresponds to the regions, to the wavelengths at which strong absorption is observed. When we see this behavior of n, we have to compare this behavior with behavior of v, and as far as n is c on v, it looks strange that for some region here we see that n is less than 1, and how it is possible? It can be less than 1 if v is greater than c, but according to the theory of relativity, it is not possible that speed exceeds speed of light. Here we need to say that actually the theory of relativity says that there is no possibility to transfer any signal with a speed exceeding speed of light. But here we see that this v, it is phase velocity, and you cannot, if you have infinitely long wave without any difference in any oscillation, this wave contains no information. So imagine that you need to send some signal from one point to another point. If all the time you have some wave, you don't know whether at this point something happened, because this wave is all the time the same. If you need to transfer signal from this point to that point, you need to do something with this wave. For example, to stop it, or to change the amplitude or something else. Any change in this wave result in existence of many different waves due to expansion in Fourier series. And in this case, we have already different waves with different frequencies and wavelengths. And as we know from the previous part of the lecture, it corresponds already to group velocity. And for group velocity, in the case that n is, here we have the part of normal dispersion. For normal dispersion, we have dv over d lambda 0, sorry, dn over d lambda for normal dispersion is negative. Then dv over d lambda will be positive, and then u will be less than v. So again, nothing will happen, which contradicts to the theory of relativity.